Okay, good morning. Welcome to VSPG. Today we have a presentation from Dr. Benjamin Mills from the University of Leeds. He's presenting on models for Earth's climate and biogeochemical evolution over the Precambrian. Andre is going to introduce Benjamin for us. Go ahead, Andre.
Yeah, it's a pleasure to introduce Ben. Ben did his PhD with Tim Lenton and Watson, and when stayed for postdoc with Tim Lenton and short postdoc with Andy Richwell in Bristol before he took position in Leeds. And since his PhD, he was interested in interaction between climate and biogeochemical cycles, first in Phanerozoic and then extending into Precambrian. And I guess that's the topic of his talk today. So with this, I pass to Ben.
Thanks very much. Yeah, thank you very much for having me. Really great to talk to you all. So I'm going to talk about models for Earth's climate and biogeochemical evolution over the Precambrian. Now, this is obviously very broad, but I think the broadness of it sort of encapsulates how little we know with the modeling, with the major kind of quantitative changes over this time. So what I'm planning to do is I will talk briefly about key environmental changes over the Precambrian. So these are the kind of things that we want to try and capture with our models. Then simple quantitative modeling of the long-term system evolution. So just attempting to get the various changes of what goes up and what goes down and what stays the same over very long timescales. And then finally, I want to talk a bit about spatial continuous modeling for deep time. This is something my group does a lot more over Phanerozoic time, but it's something we really want to start extending into the Precambrian. It's something we're working to do now. So I'll show you a little bit of that. Okay, so first thing, key environmental changes over the Precambrian. So I'm going to talk about a few very basic things that we think we know about Earth history. So first off, the temperature of the planet. So there isn't a very good or well-agreed proxy for the temperature over sort of 100 million year, billion year timescales. But what we do have is a relatively consistent record of glaciation. So I think from this, and so these blue bars here are the glaciations, what we can tell from this is we don't appear to have a clear trajectory in temperature over billions of years. So it's not as if the Earth was extremely 70 degrees or so C hot, and then it cooled down. It doesn't seem to be that it was locked in ice and then it thawed. It seems to be temperature has varied potentially around similar sorts of levels as today throughout all of Earth history. We obviously don't know the entire extent of those variations, but there's not a clear trajectory there in temperature, I would argue, at least. In atmospheric O2, there is a clear trajectory. We're very, think we have a very good idea that oxygen levels are very low before the Great Oxidation, so Paleoproterozoic and before. This is because of the absence of well, it's because of mass-independent fractionation of sulfur, which shouldn't really happen when we have an ozone layer. So we're quite certain about this constraint. The other constraints are a little more shaky, but we're pretty sure that oxygen rose quite a lot, several orders of magnitude during the GOE. We think it probably didn't get to present-day levels because we don't oxygenate the majority of the ocean basins. We think that eventual oxygenation happens at some point in the late Precambrian into the Phanerozoic, and we'll finally have enough oxygen to burn things in sort of the Devonian, Ordovician, Silurian, early to mid-Paleozoic. So in terms of broad trajectories over time, oxygen seems to be going up. Phosphorus burial. So this is a record of phosphorus weight percent in shales over time. And again, I'm going to do time, I'm always going to do time this way. So if you're used to seeing this record, it's probably flipped. But this also goes up over time. So low fractions of phosphorus in the Precambrian and more as we come into the Phanerozoic. Carbon isotopes do not go up, right? So they're famously invariant. If we look at delta 13C of carbonates here and delta 13C of organic matter, they tend to hover around the same value for all of Earth history. This is, of course, part of a famous paradox of why is this not changing if so many other things are. The solar flux, something else we know is that the sun is getting brighter. In fact, this is the thing with the most confidence out of everything. Is that due to sort of standard main sequence star evolution, the sun has got brighter and brighter and brighter over time. What this means is that if we didn't have changes in greenhouse gas concentration, we'd expect a very cold Earth from sort of the Mesoproterozoic and beforehand. But that doesn't seem to have happened, and that is because we think we know that atmospheric CO2 has come down as the sun has brightened. So although these early proxies for CO2 and these paleosol proxies are very uncertain, this line through the middle is actually a model, but we're fairly sure that CO2 concentrations have come down as the sun has brightened. And then finally, the input rate of CO2. We're reasonably sure that this has probably come down over time as well. So this is based on there being a hotter early mantle, faster plate tectonics, faster rates of spreading, so potentially higher inputs of CO2 at mid-ocean ridges back on the early Earth than you have on the present day. Now, I've gone through those things relatively quickly, so I'm going to try and summarize really what I'm talking about here in a single slide. So the key environmental changes that appear to have happened, so this is sort of over the Precambrian, pretty much up until the present day, but very much between sort of the Archean and the mid-Paleozoic. We've had the solar flux has gone up, the amount of phosphorus that we're burying in shales and sediments has gone up, and the amount of oxygen in the atmosphere and the oceans has generally gone up. Meanwhile, the global average surface temperature has not had a sort of general trend. It hasn't really gone up or down. It seems to have oscillated around potentially similar values. This is the same for delta 13C. There's no clear trend up or down. It appears to have oscillated around similar values, largely around 0 for carbonate 13C. And then we have things that have gone down. The gassing input of CO2 appears to have come down over time, and the actual amount of CO2 in the atmosphere itself also appears to have come down over time. So these are those basic sort of metrics, 7 things that we were hoping to try and match in our sort of theoretical understanding of how this system works over long timescales. Now, within these ups and downs are some well-known paradoxes. So this paradox here of the delta 13C versus the oxygen. So delta 13C records the amount of carbon 13 versus the amount of carbon 12 that is being buried in sediments over time. Now, photosynthesis produces carbon that is more lightly fractionated, so it's more carbon 12, which means that the more photosynthesis you do, this ratio in carbonates becomes heavier and heavier and heavier, because this is the inorganic sink. So you might assume that if we're doing more and more photosynthesis over time, we're burying more and more carbon, we're producing more oxygen, we might expect delta 13C to be on a constant rise over Earth history. But this isn't the case. It is, famously invariant over long timescales. So this has been a bit of a problem in the literature, first outlined quite a few decades ago now. But in the last decade or so, we feel like we're coming to a solution for this. So this is based on what else happens in the organic carbon cycle, which is the oxidation of fossil organic carbon. So this is a plot here of oxygen concentration in present atmospheric level. And then this is a model. This is a model for oxygen penetration into the soil and the weathering rate of organic carbon for different erosion rates. So if you have very slow erosion, then your organic carbon weathering rate is largely insensitive to oxygen concentration. It's just about how much you can get into the weathering zone. If you have very, very high erosion rates, you start to become sensitive to O2. You start to put more organic carbon, more fossil organic carbon into the weathering zone than you can actually weather, even under quite high oxygen concentrations. This it holds out versus some observations at the present day. And what this generally means that if you plot the distribution of these different erosion rates, at least at the present day, you get something a bit like this, which is PO2 in PAL again, this time on a log scale, versus your oxygen consumption through oxidative weathering. And basically what it seems to suggest is that it's oxygen dependent. So if we were to go down to a 10% PAL, we'd reduce the oxidative weathering rate by a fair whack. And if we were to go down even further, we'd reduce it even more. Now, what this means for the delta 13C hypothesis is that if we imagine an early Earth with low oxygen concentrations, we're not going to be weathering as much organic carbon, fossil sedimentary organic carbon. Now, this is the stuff that's very light delta 13C. It's very lightly fractionated. So if we're not weathering as much as of this, then the overall carbon that we're inputting can get heavier and heavier. So what this means is that in order to preserve that heavy delta 13C signal over time, you can do this by either having a lot of photosynthesis, a lot of burial of light carbon, and a lot of weathering of light carbon, i.e. the present day, Or you can do this by burying a lot less like carbon and also weathering a lot less like carbon. So we argued in this paper, and several other people have done similar studies following this paper, that this is a feedback on delta 13C, that actually whatever your oxygen concentration is, if you bury more organic carbon, what we're going to do is ultimately weather more organic carbon. So the delta 13C is going to be heavily buffered against that. So we think that helps to explain why 13C is largely invariant over Earth history, certainly on those sort of 10, 100 million year timescales. So that's one paradox we might not have to worry about as much. Another one is this combination of decreasing rates of degassing and increasing rates of oxygen. So this is a difficult one, because if we imagine an early Earth where we have a huge amount of carbon input, so a very active mantle, lots of spreading, lots of CO2 coming in at ridges, we're going to have to get rid of that carbon, because what happens on the Earth is it has this natural thermostat. This is the silicate weathering thermostat. Can I just check that this thing, is that box over your screen? Well, it's gone now. We know this.
Okay, sorry. It looks good.
I haven't said anything. I should have just got rid of it. What we know, certainly over Phanerozoic in more recent time, is that silicate weathering is sensitive to things like the amount of water in the atmosphere, the amount of CO2 in the atmosphere, and the temperature of the land surface and of the atmosphere. So what happens is when you have a lot of CO2 in the atmosphere, you enhance this silicate weathering process. Now, what this does is it draws down atmospheric CO2 to make carbonic acid in the rainwater. This then mixes with the silicate rocks, and you end up taking bicarbonate into the ocean along with some of that atmospheric CO2. And ultimately, when you form carbonate minerals, you sequester some of that atmospheric CO2 on the seafloor. So this is your sort of traditional silicate weathering feedback. And this is how we think the Earth really has maintained its habitability. If CO2 degassing is very high, you have a lot of CO2 coming in, then weathering processes accelerate, the Earth gets very hot and very wet, and you start to remove CO2 onto the seafloor. So this is all very good for maintaining surface temperature, but what this potentially means on the early Earth with a lot of CO2 degassing is that you're going to do a lot of weathering. And if you're doing a lot of weathering, you're going to be inputting a lot of nutrients into the ocean, which means you're potentially going to be doing a lot of photosynthesis and burning a lot of organic carbon as well. So if we go back to our arrows here, very high early Earth degassing rates versus very low oxygen could be difficult to do in a model. And this has proven difficult to do in simple box models for this reason. If you have high degassing and you have high CO2, then you just expect a lot of phosphorus coming into the ocean, which, if it's full of cyanobacteria, you would expect to result in a lot of carbon burial and a lot of oxygenation. So this is a potential paradox that we're going to have to get around with what I'm about to present. So, okay, so those are the key environmental changes and perhaps some of the issues wound up with them. And what I want to introduce now is simple quantitative modeling of the long-term system evolution. So these are simple box models that we develop, and we try and run these cycles through time. So we're talking about the carbon cycle, the oxygen cycle, the phosphorus cycle, predominantly. We're trying to start off on an Archean Earth. We're trying to run these through time to the present day, and we're trying to create broad 100 million year trajectories that just look something like we see in the geological record. So I'm going to start with a model that we published about 4 years ago now, 4 and a little bit years ago, which is sort of the attempt here is to include the minimum amount of stuff that we need, so the model can run quickly, but also to include enough complexity so that it can do the important things. So here we have a carbon cycle. So the whole thing is built around a 4-box scheme where we have 2 boxes on the shelf. So our proximal zone and our distal zone, we have an open surface ocean, and we have a large deep ocean reservoir. This is so we can approximate the idea that, of course, most biogeochemical processes are actually happening on the shelf. But this is a huge reservoir of things like oxygen. So here's our carbon cycle. We've got explicit productivity and mineralization. So we take our dissolved inorganic carbon, we turn it into Sea orbs, photosynthesis. We then do exploration and we remineralize it, and we can bury organic carbon. We also have a phosphorus cycle, which again, we turn reactive, soluble, bioavailable phosphorus into organic phosphorus. And then we also mineralize that back to the ocean pool when we do our respiration. And then we can bury phosphorus. If we bury organic matter, it's going to take phosphorus with it. We can also bury it as iron-bound phosphorus or as calcium fluorapatite. And then finally, we have an oxygen cycle. This is a little less detailed than the other cycles. We just assume that all the surface ocean oxygen, mixed layer, and atmosphere all lives together in one box. This represents, I think, less than 1% of all the oxygen on Earth. Anyway, most of it is in this big deep ocean box here. So this is how we chose to represent the system. And in this early model, we weren't so interested in the inorganic carbon cycle and the climate and the temperature. We just wanted to see how this system would react to varying global redox, i.e., would it do things like a great oxidation event? Would it do catastrophic marine oxygenation? Is the marine oxygen and carbon and phosphorus cycle stable over time? So those are the kind of questions that we were asking with that model. I'll just briefly go through what we actually found out when we ran this model. So it was a bit of a thought experiment. We didn't do any real Earth processes. We just had a sort of amount of... Oh, hello, sorry.
Hey, Ben,
Yes.
we lost you for a second, I think.
Oh, I'm so sorry. Am I back?
Or was it me who got lost? Sorry, can somebody else speak up? Sorry, was it my internet?
It's fine. Yeah.
Okay, sorry, it was my internet issue. Sorry.
So it's best to say, though, because I know people who've been given a seminar for half an hour, not realizing that their internet's dropped out and then no one's even hearing them.
Yeah, it's an issue where, that happens on both sides. Sorry, keep going.
That's fine. I need a drink anyway. So this was a thought experiment. We just put different amounts of reductant into the model. So we just treated that as hydrogen, and we just blasted in various amounts of hydrogen and ran it to steady state. Now, of course, if we're putting in reductant, we expect it to consume oxygen and the oxygen levels to become lower. But what was quite nice is that we found out that we can get these sort of critical transitions that we see in the real system. So I'll explain it starting from the anoxic side. So with loads and loads of reductant coming in, there isn't really any oxygen anywhere because we're consuming it all. Now, as we start to put less reductant into the system, we start to oxygenate the atmosphere. And we get this transition here, which is when initially we're controlling this atmospheric oxygen reservoir by oxidizing our reduced gases. Once we overwhelm that reduced gas sink, we then transition to oxidizing things like organic matter. And in our model, this is what causes the great oxidation. So this is broadly similar to some other views about how the GOE is driven. This isn't a dynamic model, this is steady states. So we don't really capture the sort of instability in actually doing it. There's no actual methane in this model, for example. There's no sunlight fluxes or anything like this. But we do capture the idea that you can regulate oxygen in two different states, depending on whether you're regulating it with reduced gases or whether you're regulating it with sedimentary organic carbon, weathering that instead. So that was okay, but that wasn't really very new. This has kind of been done before. What was more new is we got these catastrophic oxygenations of the ocean. So first in our more proximal ocean zone, then in our more distal zone, and then finally across our deep ocean. And we did this due to nutrient and oxygen feedbacks. So the idea is that when you begin to oxygenate a sort of deeper body of water, you start to draw down phosphorus. Start to make things like iron oxides available, and you can remove phosphorus from the system. If you start removing phosphorus from the system, the immediate thing that happens is that you cut off productivity. Now, if you cut off surface ocean productivity, you cut off your sinking flux of organic carbon, you're just going to lead to more oxygenation because you don't have all that reduced material to power respiration. So you can drive this kind of catastrophic oxygenation of the water column just by gradually feeding it more and more oxygen. So this is kind of the opposite of an OAE, of an oceanic anoxic event. So within an OAE, the idea is that you deoxygenate the water column. This allows you to regenerate nutrients from the sediments, drive more productivity, and sort of fuel more eutrophication and deoxygenation. This is exactly the same thing in reverse. It's sort of like the end of an OAE. So I thought this was kind of interesting. You see there's got breaks in the lines here as well. So between the sort of steady states, you have these unstable states where the model didn't have a steady state. And when we zoomed into this, we found what is happening is an oscillation. And this is because there are two different cycles going on in this model. There is this positive feedback of where we say we oxygenate the water column, we retain more P in the sediments, we cut off net primary productivity, therefore we don't use as much oxygen in the water column, and it goes round and round until we have much more oxygen. This is then modulated by longer term negative feedback, in which if we're not doing this productivity, if we sustain this over millions of years, we're not going to bury the organic carbon. And if we're not doing this, we're cutting off our long-term source of atmospheric O2. So you can see in this graph that as we deplete the ocean in oxygen here, We then slowly start to deplete the oxygen in the atmosphere up here. And once this gets a little bit lower, we don't ventilate the ocean as well. And therefore, so this is Foxic. Once we change the amount of oxygen in the atmosphere, it's here, right? It's increasing here. Sorry, I'm not very good at these colours. The atmospheric oxygen is increasing here as we're in the anoxic phase. Eventually, we reach the point where we start to oxygenate the ocean, and we do this catastrophic positive feedback in the other direction. So this is kind of how people have envisaged an OAE event happening over these kind of several million-year timescales. Depending on how strong we think the different fluxes and feedbacks are, we can get various different timescales out of this. But this seems to be something that comes out of these simple models, and the idea is maybe explain some of the instability we seem to see in the later Precambrian and early Phanerozoic. So particularly you have these sort of pulsars of redox-sensitive trace metals being deposited in various basins. And of course, you have actual OAEs that may follow a similar sort of structure. So that paper was all about the sort of dynamics between organic carbon, oxygen, and phosphorus. We did manage to produce some acceptable looking oxygenations of the atmosphere over this time. But we did this just by imposing a simple curve of reducing reductant input or arbitrarily increasing the weathering inputs of phosphorus. So we sort of skipped all of these paradoxes because we were allowed to just have different amounts of reductant coming in without weathering more phosphorus. And we were allowed to weather more phosphorus without worrying about things like climate and CO2 and stuff like that. So this was a very sort of largely incomplete model. It made some interesting predictions for why you might have catastrophic transitions in oxygen at various points in Earth history, but it didn't really solve this issue of how does the planet actually work on long timescales. So in terms of these ups, downs, and stable things, that model ignored all of these things. There was no solar flux, there was no surface temperature, there was no thinking about delta 13C or isotopes, there was no CO2. All there was degassing of hydrogen, phosphorus burial, and oxygen. So what we've been working on the last few years following that paper is to try and add more things into it, to try and make it, to take that sort of broad framework that encompasses the phosphorus oxygen feedbacks and to include things like climate, CO2, and inorganic carbon and carbon isotopes. So these boxes for organic carbon, for oxygen, organic carbon, and phosphorus are largely the same. What we have added is a global representation of how much CO2 is in the system. We've got fluxes of weathering, we've got carbon burial, taking CO2 out of the system, seafloor weathering, reductants coming out of volcanoes. So all the kind of geocarb style stuff that you would usually see in a model for climate and atmospheric CO2 over very long timescales. So the idea here is to try and reconcile exactly what is going on with all these fluxes over Earth history. Now, in order to run this over long timescales, we had to impose some kinds of external forcings. So these are the things we decided we would put into the model. So this is our degassing rate. This is taken from the Hayes and Wilbauer paper I showed earlier. We put very large uncertainty on all of this because we really don't know these fluxes very well. So degassing rates could have come down a lot over Earth history, or maybe they stayed broadly the same. We don't know. So we're going to throw in the entire range. Similarly, exposed landmass, this is the exposure of the continents. A lot of argument about exactly how this happens, but there's a sort of general agreement that at least in the early Archean, you probably had less exposed landmass than today, although exactly how this proceeded is unsure. So again, we've tested all the space here. Either we can have no continents and a rapid exposure here, or we can have very little change over the Archean. Another thing that's uncertain is to what degree biology impacts continental weathering. So this is largely something we think happens during the plant colonization in the Paleozoic, but we don't really know what happened. So there could have been a large increase in the weathering amplification from biology, or maybe there wasn't at all. So again, we're throwing the entire uncertainty range here into the model. And then the final thing here, this is now in blue because we didn't think of this initially. So what I'm going to take you through is how the model responds to the pink forcings, and then I'm going to talk more about the blue one. But what the blue one is the relative crustal carbon content of the crust. So this is carbonate rocks, just how much carbonates you find in the crust over time. Because if you go back to the early Archean, you look at the primordial crust, there are carbonates precipitated in it largely. It's a silicate crust. Whereas if you go to the present day, you have this huge buildup of carbonates and also of organic matter that's now in the continental crust. So this is something we've sort of uncovered for ourselves at least, is very important. Now, there are, again, some papers that have previously talked about buildup of carbon in the crust, again, Hazel-Wallberg paper, being very important for oxygenation. But this is, I think, the first time it's been included in one of these dynamical models that tries to sort of do everything from first principles. So first, I'll take you through what happens in the pink model. So this is where we have degassing rates either going down or constant, we have a little bit of continental emergence, and we have some ambivalence about biological weathering. Now, we do get some things that are okay. So if we look at 13C, it's relatively stable. So the feedback that I talked about earlier about weathering organic carbon, and this being a sort of stabilizing feedback on 13C, this seems to be doing very well. Because actually, if you look at oxygen here, we've actually got similar levels of atmospheric oxygen in the present day, and we're maintaining a similar amount of 13C. So it's broadly a similar sort of present day situation we're getting back here. CO2 is following an upward trajectory for two reasons. The sun is less bright, so this is having an effect on continental weathering rates. Also, our CO2 inputs are largely higher than the present day. So we've got a lot of CO2. Got a very hot surface temperature, 40, 50 degrees. Well oxygenated ocean, because we're doing all this weathering. It's very hot. We're doing an awful lot of continental weathering. We're putting a lot of nutrients in. You can see we're burying a lot of phosphorus in the model, more than is indicated by the record. And we have high atmospheric oxygen. So this is overall a pretty poor fit to the geological record. Effectively, what we are doing is taking the Phanerozoic Earth and we are running this through time. And the only thing that's really changing is the degassing rates of things are going up. So we do have more reductants coming in, but it's not enough to overwhelm what's happening with the amount of CO2 that's coming in, that the climate warmth and all of that weathering of nutrients and burial of organic carbon. So it doesn't work. Now, the next thing I'm going to explore is what happens in the model if we now include this reservoir of crystal carbon. So what this does is that a lot of CO2 degassing at the present day comes from remobilizing carbon in the crust. Also, a lot of weathering fluxes like carbonate weathering come from crystal carbonates and weathering of organic carbon as well. So a lot of the inputs of carbon into the surface system are one way or another carbon that was already buried in the continental crust. Now, if we take this into consideration, our model suddenly starts to look a whole lot better. So I'll go to 13C last, but we now, because we have less carbon in the crust in the early Archean, even though we've got a faster spreading rate and a hotter mantle, we're not mobilizing as much carbon as we were. So we're mobilizing enough to keep it warm, but not enough to make it super hot. So our temperatures over Earth history, if we look at the bottom right here, are largely the same as the present day, although they do get very low here. So we assume that the carbon in the crust tends to zero here, which may not be very accurate. There may be other processes we need to consider in the earliest Archean. But aside from that, it's looking relatively okay. Now, the sort of cooler Earth with less carbon recycling, less delivery of nutrients into the ocean, now permits lower rates of organic carbon burial. So we've got a lot less phosphorus being buried here, more consistent with the record, and we have lower atmospheric oxygen. Because of this feedback on 13C, even when we have low atmospheric oxygen and low productivity, because we're weathering a lot less organic carbon as well, we can maintain roughly static 13C over Earth history. So this does relatively well in this. So what we get here is a great oxidation. It could be, in the model, it's anywhere between 3.5 and about 2. So the real GOE is sort of contained in there somewhere. But we're exploring such a large parameter space that we're less concerned about this being wrong. We're just quite happy to have the broad trajectory in the right direction. We feel this is quite a nice advance. Hopefully sort of models like this will let us explore things in a bit more detail. So, we've got the Lomagundi excursion here. Having a background model that seems semi-reasonable each side of it might help us do a bit more work on this. Obviously, we have the Mesoproterozoic, lots of things happening in the Neoproterozoic as well. So, and that paper is currently in press, Nature Geoscience. So you should see this out in the next few weeks. So yeah, interested to hear what everyone thinks about it, really. So that was our simple quantitative modeling of the long-term system evolution. So I think we're kind of getting there with this now. We have these simple box models that can do a lot of stuff that seems realistic in the carbon, oxygen, phosphorus cycles over very long time periods. And what I want to move to now for the last kind of 15 minutes or so is a kind of modeling that we're doing with the Phanerozoic. Because we've got a lot more detail in the Phanerozoic. We know about paleogeographies. We know more about climate. We've got a lot more proxies. So we can use much more complicated modeling approaches. However, there's a limit to how complex we can make our models due to our sort of computational demands. So this is something I'm just calling the timescale complexity problem. This encapsulates the idea that we can have like a 3D Earth system model. It can have lots of really accurate processes in it. So we've got energy balance, moisture balance, atmospheres, 3D physical climate. We can have 3D biogeochemistry. We can have all sorts of lovely stuff. So we can have accurate processes. But if we have accurate processes, we end up running the model for short timescales. So models that include climate and biogeochemistry in 3D typically cannot be run for more than 1 million years and cannot really, feasibly be run for more than a few tens of thousands of years if we start to switch everything on. So the models are fantastic. They're teaching us an awful lot of stuff about sort of spatial interpretations of global biogeochemistry and climate, but we're not going to be able to run one of these models over, for example, the whole Phanerozoic or over the whole of Earth history. In order to do those longer timescale model runs, we have to use the box models. So this is what I've been using before, simple representations of carbon existing here and carbon moving to there. We're able to make them a bit more complicated with different regions of our ocean, like I showed, and a few more explicit processes, but we're not going to be able to involve proper 3D grids. So what I've been trying to do in my group over the last few years in Leeds is to build a kind of model that sits between these frameworks. So ultimately a box model that can run for billions of years, but something that incorporates a lot of 3D architecture that we have in these more complicated models. So this is what we call the SCION model. It stands for Spatial Continuous Integration, which means that it has spatial components in the model, but it can also be integrated continuously over millions or even billions of years. The way we do this is we have a steady state GCM climate. More on this later. So we don't actually solve any of the physics. We just have a 3D climate that is controlled by the other model variables. This means we can include a 2D topography, hydrology and surface processes, so things like weathering. We can also include a 2G dynamic vegetation model for our Phanerozoic stuff. So we can have actual vegetation that lives in the different grid cells and does carbon cycling and that sort of thing. At the moment, we're still using single box marine biogeochemistry for this model, but we will update this soon to have more boxes. The way this works is the bottom part here is your sort of traditional box model. So we've got a carbon cycle with organic carbon and carbonate and CO2. We've got an oxygen cycle, a sulfur cycle with sulfate, and we can bury sulfur as pyrite or gypsum. We've got a phosphorus cycle, a nitrogen cycle to drive our productivity. And then we have, at the moment, a strontium cycle, just to look at strontium isotopes, because I like strontium isotopes. Now, this is similar to things like COPS and geocard and other models you might have seen. Now, what is really different here is what we do to figure out the model climate. So at every model time step, we take the current CO2 concentration and we feed that into a climate model emulator. So the emulator is built by running a climate model lots and lots of times for lots and lots of different continental configurations and lots of different CO2 levels. And this means that we can interpolate between CO2 levels, we can interpolate between continental configurations. So at any point in our model, we can very quickly ask the computer, what does the climate look like at this many years before present and under this much CO2? And it will give us a 2D feel of what it expects the climate to look like without actually running any of the physics. And this means the model can run very quickly. Now, another thing that helps us do this interpolation is machine learning and deep learning approaches. So this is something called film, frame interpolation for large motion. So this is a machine learning technique that's often used in the film industry to speed up footage. So to put more frames, to put missing frames into footage. So this can increase your frame rate if you want to do that. And it can help you with animation. So you don't have to draw your cartoon characters moving each frame. You can interpolate between them using machine learning. Now, the way this works is it takes input pyramids, which are looking at the snapshot. So you might imagine like a screenshot of a film. It looks at screenshot A and screenshot B. It looks at various different versions of them in different resolutions to try and pick out features that are big and features that are small. It then uses this convolution approach where it arbitrarily amplifies different parts of the image in different ways and puts this into a neural network. Then using the neural network, it estimates the flows between the images. So it takes one image, it takes the other, and it tries to figure out what should go in between. Once it's figured this out, it gives you an output image of what the neural network thinks should go in between. Now, of course, when you do this initially, it's absolute garbage. But what you can do is you can train the network on, and this one has been trained on hundreds of thousands of videos, in order that the equations it uses in the neural network start to give you outputs that actually look like the intermediate frames of videos. So this has been really useful for this kind of work, because it means that if we have a climate simulation at, say, 300 million years ago, we have one at 310 million years ago. If we were one at 305, we can very quickly ask this algorithm to generate one, and it can do so very quickly. And it tends to follow the continental motion between these frames. We have a method for this currently in review at Dynamic Modeling, GMD, Geoscientific Model Development, if you want to go check out that. The reviews are still open, so if you really hate this method, please go and write a review. We'll try and make it better. But what that allows us to do is to run the model like this. Now, I apologize for the white screen here when everything else was black. I was actually doing another model run earlier, but it didn't finish in time. So this is a continuous model running over the Phanerozoic. So you can see the continents are moving in sort of real time. We're generating climate, we're generating runoff, which means we can calculate things like silicate weathering. So this CO2 record is being dynamically calculated by the model. We're not imposing any of this. We're imposing the tectonics, we're imposing the amount of CO2 degassing, but everything else is being done by the model. And I'm not plotting the biosphere here, but there are plots somewhere that show how the terrestrial biosphere is sort of spreading across the surface and doing different stuff. So this is quite an interesting thing to do. It's something we've only just started to work with. And of course, what this lets us do is to map things like silicate weathering and nutrient delivery and continental processes more accurately in 2D. So we can get an estimate of how we think climate and biogeochemistry evolves, at least over Phanerozoic time. We think in a much more accurate way than we could from previous dimensional models, where you didn't have this sort of spatialization of processes. How do I get off this? So this is currently what those model predictions look like over Phanerozoic time. The model is also very quick to run, so we can run it 10,000 times, or I think this is 1,000 model runs, and we can test the uncertainty in various parameters. So this is the model attempting to reproduce the Phanerozoic temperature curve. It's okay, it's not terrible. It is better than the previous box models that came before it, which is nice. This is the model ice line, because we have actual glaciation in the model happening at certain times. We can actually track where the ice caps are over time. So we kind of get the late Paleozoic ice age here. We kind of get the Cenozoic ice age, and we get a hot sort of greenhouse Mesozoic, which is nice. Our early Paleozoic is much worse. We have ice through most of it, so the model is much more uncertain back there. CO2 proxies, we're generally higher than the proxies, but the model has a very high and low climate sensitivity at the moment. So we're trying to remedy this with new paleogeographies and new climate model runs. But at the moment, it's looking okay. We're kind of happy with how this is doing. And it's letting us explore a lot more processes than we'll be able to with the sort of simple dimensionless approaches. So what I want to quickly go over is, because this isn't really supposed to be a talk about the Phanerozoic, it's supposed to be Precambrian stuff. So I want to briefly talk about how we're now trying to extend these ideas into the Precambrian. So we do have plate models for Precambrian continental configurations, Precambrian degassing fluxes, and we do have some climate model ones that have been done for various points throughout the Neo-Proterozoic. So I'm sorry, these are very small, you can't really see. These are just runoff maps. So this is 825 million years ago, so you've still got sort of supercontinent, Rodinia, and you have the breakup phase through here. Now, using our algorithm to interpolate between these climate model runs and using the degassing rate we have from the tectonics, we can then attempt to run our model now through Neo-Proterozoic time as well as through the Phanerozoic. And this is the kind of thing we get at the moment. Now, the first thing to note about these plots is that our Phanerozoic is actually worse. Now, this is because I've used a tectonic degassing rate only based on the spreading rate, because for the Neo-Proterozoic, we haven't made a very good estimate of the degassing rates yet. So it actually degrades the Phanerozoic predictions a little because we don't use as good a degassing rate. But we will fix that at some point. But I think it's relatively interesting what this model does for the Neo-Proterozoic. So we have atmospheric oxygen fluctuating between about 5 and 12% of the atmosphere. So potentially around that kind of boundary where we might start to oxygenate or deoxygenate the deep ocean. Our CO2 and surface temperature is broadly high, but we do have this big decrease through the turning into the cryogenian. Now, this is because our current tectonic model has a big reduction in spreading rates over this time. So a new paper out just this year, I think, or last year, from Dietmar Muller's group in Sydney, which explores this in more detail and how perhaps this is something to do with the initiation of the cryogenian snowball Earths. Important to note, this model doesn't actually do a snowball Earth. It gets very cold, it gets very glaciated, but we don't actually have enough climate dynamics in the model to allow it to do any of these traditional sort of hard or soft snowball approaches. But it's, you know, a relatively interesting thing to do, I think, nonetheless. What we do less well on is these isotope predictions. So we've got a broadly static 13C all the way through the Neoproterozoic. We're not capturing these big swings. Now, we might expect this because these swings are associated with, of course, the glaciations and potentially with the aftermath of the glaciations themselves. So it may be that there's a very good reason why we're not capturing this, but it's certainly something we should look into in more detail. Strontium isotope record, we're getting some hint of the changes in strontium isotopes over time. But again, we haven't yet got different lithologies with different strontium isotope compositions into the model yet. So it's certainly something that we can start to do, i.e. making things like lips and mafic parts of crust much less radiogenic and making old granitic areas more radiogenic. And that might help us to further resolve things in the strontium isotope ratio later on. And finally, just a little look through some of the climate snapshots. I don't have time to make a video for this. I'm sorry, I am going to make one. Again, some of this is okay, some of it is less okay. So we do get some glaciation about 720, which is nice because that's the thing that happens. We have a warm climate beforehand, but unfortunately we do predict a very cold Tonian period, which doesn't seem to be something consistent with the record. These are our continental temperatures over time, again showing cold when it's glaciated, and these are our continental silicate weathering rates, again showing a sort of enhancement, a little bit of enhancement of weathering with these low latitude microcontinents, but not enough to drive the glaciation, it seems, by itself. Okay, so I think I'm about done. I'm just going to go through a few things that we can conclude through this work, a few kind of future directions. So looking at this Scion model, so that the spatial model, looking at how this deals with the Neoproterozoic, there's clearly a lot of stuff we still need to learn. So although these models seem okay at doing broad Phanerozoic changes, they're still not brilliant in the Paleozoic, and then they're even worse for the Neoproterozoic. But, you know, our oxygen concentrations we predict are maybe consistent, so perhaps the same as the earlier Paleozoic, perhaps broadly consistent with an anoxic deep ocean with periods of penetration of some oxygen to lower depths. Our average surface temperature doesn't do anything crazy. It is consistent with there being glaciation at some points during the era. But we don't really get the deep glaciation of the Cryogenian, and we also have this Tonian icehouse, which doesn't exist in the real world. And then for our isotope trends, we get some broad replication, but we don't get any of the variability on things like a 10 million year scale. Certainly not those big swings we see in Delta 13C around and through the Cryogenian. So why is the Tonian too cold? So this is probably the worst part of the model. There are various reasons why this could be. So our paleogeographic maps we're using are currently older ones. Also, our climate model runs are currently from an older climate model. They're from foam, the fast ocean atmosphere model. The weathering enhancement from these configurations may just be too high. It may be that if we use a modern paleogeographic configuration and a modern climate model, we might find we don't do as much silicate weathering and the climate is warmer. It may also be that our degassing fluxes are not very good. They're very simplistic. They're only presented by the slab flux at the moment. As I showed, when we do this for the Phanerozoic, it degrades the model predictions anyway, so it may be expected that without a good estimate of CO2 input rates through the Cryogenian and the earlier Neoproterozoic, maybe that's why we're not doing so well. So this is, again, something we're working with at the moment with the G-plate model to try and get a better idea of combined carbon release from all the different kinds of plate boundaries in the model. And then finally, maybe there are some missing biological factors. We don't consider things like a transition from cyanobacteria to algae dominating primary production. We don't really consider sort of evolution in our biosphere where our biosphere lives. At the moment, it's just non-dimensional. You pour phosphorus into it, makes organic carbon and oxygen. So there may be a lot of work to do there as well. I came onto this a little bit. Why is the 13C record so stable in the model? Well, we haven't actually got snowball Earth. So any attempt to run a model through the Cryogenian that doesn't at least produce something that looks like snowball Earth in the record probably isn't going to do things that are very realistic in other proxies. So perhaps some idea to parameterize what may happen during snowball Earth in this model will lead to a better recovery of 13C. If these events do terminate in some sort of super greenhouse aftermath, that can certainly be something we can imagine raising the 13C ratio, inputting a lot of nutrients into the ocean, that kind of thing. Potentially testable in this model. The carbon cycle may be fundamentally different in the Precambrian, so this idea of much more dissolved organic matter, sort of in an oceanic soup before we oxygenate the deep ocean. Could that have changed the model behavior? Again, something we can potentially look at. And then missing biological factors pre-cryogenian. You know, I haven't mentioned at all what existed on the land surface before plants. Was there bacterial mats? How productive were they? Where did they live? Again, something that is certainly testable with this kind of model, especially since we have a spatialized terrestrial environment, but not something I've actually tested yet. So I know I'd like to come to the end of a talk where I kind of try and answer questions, but this is very much one where I'm just asking questions. So broadly, this is I'm going to summarize now. I think I'm done. What is nice, I think, is that the simple box models can now give a reasonable replication of Earth's environmental evolution on the sort of 100 million year scales. So we have a simple box model for carbon, for oxygen, for phosphorus, that you can start it off in the Archean with what we think are broadly Archean constraints on tectonics and biology. You can then let it evolve towards the present day, and it will produce something that looks quite a lot like our planet over these scales. So I think that's really interesting. I think that's really great. And hopefully we can use that as a platform to try and explore a lot of other events. These more complex, what I'm calling mixed dimensional models, like our Scion model, they're quite useful for representing the Phanerozoic on 10 million year scales. So we seem to get the greenhouse, icehouse cycles of the Phanerozoic quite well in these models. This, of course, helps us better understand what is driving those cycles. We're trying to extend these into the Precambrian, but we're currently limited because we're using old paleogeographic maps, we're using old climate models. So luckily, my group at the moment, we have a big European project to do this better. So we're currently building more paleogeographies, we're currently running climate models. So, you know, I hope to be able to come back in a few years and have some much more convincing and interesting things to say, certainly about the Neoproterozoic, if not more of the Precambrian. Because yes, our model probably does a very poor job of representing what we think happens on the sort of 10 million year scale throughout the Neoproterozoic. So I think that's it. I hope you found that interesting. You know, I guess what I've tried to lay out here are some of the things that we have, some of the modeling tools that might be useful for collaborations and for thinking about other ideas and how we might learn other stuff. So I've got a little bit of time for questions. So thank you very much for having me.
All right, thanks, Ben. Great. So if you need to get going at some point, just tell me and I'll cut it, but we don't usually stop it at any point. So we'll go ahead and move on to questions. If you've got a question, you can go ahead and type it into the chat, or you can find the reactions button at the bottom and click raise hand. We have one from Greg Vitalik, so go ahead, Greg, please.
Hi, Ben. Enjoyed that. I don't see my video. Oh, there it is. Very good. I'd like to suggest the reason why your model is not picking up the carbonate del-13 signal is because that is not a productivity signal. It's a signal of sea level. Where you get the low ones, it's demonstrable that those are actually paleocasts, as in the Wanaka Formation now. Nick Christie-Blick has confirmed it. Those were actually fluvial valleys cut into it. So it's a local weathering effect that you're not taking into account in your model, which is kind of a general critique. I was surprised you didn't include the land at all in your general box models.
Sorry, how do you mean the land at all?
You have your model is entirely for the sea.
Model.
There's no box for what the land is doing, and the reason why the del-13 doesn't match your model well is because that's a very local paleocast effect on the isotopic record. Those limestones were weathered.
Yeah, I mean, I think that's a really interesting idea. So I think, you know, what I can potentially do is, you know, I would like to test things like this within this kind of model. So if the model can produce those kind of swings in the carbon isotope record through those mechanisms without having to infer and enhance productivity or anything else, And it can do so while also getting the sulfur record right and the strontium and everything else, then yeah, I think that would be fantastic. So, I mean, I think that's a great point. I would like to, yeah, I'd like to test things like that. I think it'd be great.
Yeah, well, it goes both ways. The model needs to include something on land too, because we have a long record of petagenic carbonate now, going on 2.4 billion years. And that petagenic carbonate has evidence that there was isotopic fractionation of organic carbon as well on land.
Yeah.
These are going to change your calculations quite a bit. I think you can't, assume that it was just uniform.
No, absolutely. I mean, I agree, right? Yeah. So, I mean, one of the things we're hoping to do in a new project is extend the sort of treatment that we have of the land through the Phanerozoic with the land plants and the soils, is to try and extend a treatment like that back into the Neo-Proterozoic, try and address some of these ideas.
And let me also add that I love your snowball. You're missing the snowball and you're missing the super greenhouse, because I don't see it in my studies of the cryogenian either.
Yeah, very good. I mean, I haven't, because I haven't put enough processes in this model yet, I'm not able to really conclude on which event the model supports. So yeah, I'm kind of looking forward to making a bit of headway there.
Sweet. Thanks a lot.
Thank you.
All right, thanks, Greg. Next we have Ava Stoiken. Please go ahead.
Yeah, hi Ben, great talk. So I was wondering for your Archean model, of course, obviously there are lots of uncertainties in the Archean that we don't know about, but how sensitive is that GOE to the, I guess, the age or the origin of life? So does it matter if you put it at 3.5 versus 4.2 or something like that?
Oh yeah, great question. So that model has life right from the beginning. So yes, if we removed the photosynthesis from the model, I think it would actually just completely crash and not work at all. If it was lucky to not crash, it would have more oxygen in it, because there's no other oxygen sources in the model. So absolutely, we can change the GOE of the model if we change the evolution of oxygenic photosynthesis. Absolutely. Also potentially the ratio between anoxygenic versus oxygenic photosynthesis as well. That would, yeah. I mean, again, something I'd really like to explore. I guess by giving a talk where I really haven't made any firm conclusions, I would like to explore all of these things.
Mm-hmm. I guess can you put an upper limit, or I guess a lower limit on when life would have needed to originate, and when oxygenic photosynthesis would have needed to originate to make your model work reasonably well?
Well, yeah, I mean, that's a really interesting question. That's potentially something you can look at. I have to go and find the pictures. So, well, I mean, maybe not, because if you have anoxygenic photosynthesis, you can probably produce similar carbon isotope records anyway. Yeah, that's a tricky question. There's potentially something you could do within this framework to do something like that, especially if you brought in things like nitrogen isotopes and other nutrients and stuff.
Oh, thanks.
Okay, thanks, Ava. David Catling, please go ahead.
Yeah, I have a couple of questions. One is related to your mass and redox balance. So you talked about solving your problem by accumulating carbon on the continents.
Yes.
But do you put any in the mantle? And what about the redox bounce? Because you've got a lot of reductants going in. Is there some of that being accounted for by burying organic carbon? Have you looked at that? So that's sort of my question, because I think if you talked about the Hayes and Waldbauer paper,
yeah.
And the recollection is one way that they solved their mass balance is they just stuffed a lot of carbon into the mantle. And is that happening at all in your model?
Yes, that's a great question. So in this model, we haven't fully closed the system with the deep earth. So we have made the same assumptions as Hayes and Waldbauer. And actually this buildup of carbonate in the crust is actually imposed on the model rather than happening as a result of the carbon cycling, which is a bit of a shame, really. It was a simpler way to do it. So further work, yeah, we would want to have a proper open system which included the mantle, in which carbonate buildup was an actual result of what was going on in the hydrosphere rather than just being imposed. But yeah, we haven't got there yet.
Okay. And then my second question was sulfur. At one point, you put up a delta 34S curve, but you didn't really talk about amounts of sulfate in the ocean, which is, there are constraints, at least we think, on that. But do you actually match the sulfate curve for what's going on in the ocean? And also the isotopes have two parts, right? You've got seawater and, well, I guess the pyrite is kind of all over the place. And then there's also this coupling that people talk about between the carbon and sulfur systems in the Phanerozoic, but more decoupled in the Precambrian.
Yeah, again, all really great questions. So this model, the SIO model, does resolve pyrite and sulfate. I haven't plotted the pyrite isotopes. I imagine what happens is they just stick almost exactly the same amount below the sulfate isotopes. In terms of the sulfate concentration in seawater, the model is a little bit too high compared to the record. Again, this could be something to do with how we build up pyrite and gypsum in the crust over time, which isn't really accounted for. So there's a disconnect between the Phanerozoic style modeling, where we kind of start in the Cambrian with most of the stuff we have at the present day and just let the model kind of re-equilibrate. Whereas obviously in 4 billion years of modeling, we have to let everything actually evolve over time. So this SIO model still has that sort of, it's not linked to the mantle, it's not linked to crustal evolution over time properly. So maybe that's why. But yes, at the moment there's too much sulfate. I think there's about 10 or 15 millimolar in the Precambrian, in the Phanerozoic, which is maybe 10 too high or something like this.
Right. Okay. Thank you.
I didn't plot it.
All right. Thanks, David. Jingjun, please go ahead.
Sure. Thanks, Ben. That's a wonderful talk. My question might be kind of trivial, but I just had I noticed that in one of the slides you shows the deep ocean, though remain anoxic, still have a lot of oxygen in terms of mole, 10 to the 14, I guess. So I just wonder how that compare with some of the earlier or like Earth system model in general, showing like below 10% PaFO2, you have like zero oxygen in the deep ocean. Would that transfer in agreement with the one shown in the Gini model? Or because I suppose that will determine the concentration of the oxygen in deep ocean will determine your iron-bound phosphorus and also respiration in general.
Yeah, I mean, that's a great question. So one problem that these box models have, which you don't have in a 3D model like Gini, you can just take everything out of a box and it's okay. You can just remove all the oxygen from an ocean box and that's all right. In these box models, you can't really do that. You can't get down to zero oxygen. When you start to have fluctuations of many orders of magnitude within a single time step, they tend to get very unstable and they don't like it. So we always have this issue in the box models that they can maintain low oxygen, but they can't really get to zero oxygen because they don't have an actual circulation. They don't have actual places where you can physically deplete the oxygen and keep it depleted in one place while you have it in other places. So what we tend to get is we get about, it's very similar to the atmosphere. Throughout the Proterozoic, the model here has something like 100 to 1,000 times less oxygen in the ocean overall. So that would be an average concentration of less than a micromole, I guess. So functionally anoxic, I suppose, or on average, but it's difficult to make comparisons between these single box models and what an actual ocean looks like with circulation and processes in it. And yeah, I think that's a very difficult one for this kind of modeling. I don't know if I'll ever really get around that.
Thank you.
Okay, thanks, Jingjun. Paul, please go ahead.
Yeah, 2 comments. My colleague Dan Schrag had an interesting idea about why there's no long-term change in delta C13 of seawater. And that composition is controlled basically by the relative fluxes of organic matter and carbonate in the barial flux. And Dan pointed out that The organic flux, burial flux, is basically controlled by phosphorus inputted from weathering, and the carbonate burial flux is from the alkalinity flux in weathering. And the phosphorus to alkalinity ratio in the burial flux hasn't changed over geologic time because the composition of the continental crust hasn't changed.
That's interesting. Do you think that holds? I guess that doesn't hold for carbon isotope excursion, though, right?
Yeah, I'm just talking about the long-term stasis around 0 per mil.
So
fluctuation.
A constant fraction F org, if you will, just over the whole of Earth history. Right. Yeah. I mean, it's interesting. I guess what I've got here is a model that can vary F org significantly, and it still doesn't vary delta 13C. So I guess, yeah, you could argue whether or not you need the feedback that we have in our model if you think F org never changed. But on there, didn't Berner put together or somebody, probably Volov, I guess, a big compilation of organic carbon versus carbonate over time, and you can empirically guess F org from that, and I'm pretty sure that wasn't stable. Am I right there?
Well, they have different residence times, so I don't know that you can extract that from the record.
Maybe not. Maybe not. Yeah, I mean, I think that's a good. I think that's an interesting point. I guess, my own perspective is that we have a defensible feedback in this model that allows it to do things. I guess, is there a model which will actually replicate all this other stuff like oxygen and phosphorus and whatnot while keeping F org static? I guess that would be my question for Dan if he was here.
And the oscillations, the shorter term oscillations, are more than 10 million years. I mean, the late Tonian high delta C13 lasts almost 100 million years. It's not just 10 million year. Anyway, my second comment concerns Andrew Meredith's paleogeographic models, which I need work. And the most recent versions of the model, just recently published, for example, had the Congo craton at the South Pole at the beginning of the Cryogenian and at 60 degrees latitude at the end of the Cryogenian. And yet from the late Tonian to the early Ediacaran, Congo craton is, basically continuous carbonate-dominated sedimentation, which shows that it was in the tropics during that period. So I would, urge you to tell Andrew Meredith to pay some attention to the sedimentary record as a paleo meridian indicator.
Thank you for that, Paul. Actually, I mean, that is a great point. We're actually, it's good you said this now because we're spending a lot of money to run a lot of climate models using these paleogeographies. So we want to be aware of where things are incorrect in them.
Just can't be right.
Can I make a comment here?
Chemistry of carbonate is a basic, it's basic chemistry.
Can I make a comment that there's a bigger underlying problem that the ocean crust is made up in these models. There are no constraints in them. And so when you in your model take outgassing from spreading rates in those models, it is absolutely fantasy. And so what Meredith and others don't show is they don't have constraints in the basin, and they could put as many ridges in there, whatever spreading rate they want in there. And so just be careful. Like, I don't know how, and my question for you is, how do you want to actually start to show error and uncertainty when there is just this error and uncertainty in these I'd call them paleogeographic cartoons because they're not models for the oceanic crust. They're trying to help you visualize a couple of paleomagnetic poles and some geological constraints on there. But the actual ocean crust, we have none of that preserved. And so you can put as many number of ridges as you want in there. Yeah. And so, I mean, what are your thoughts about, like, how do you translate this uncertainty from these types of constraints? Because the maps do not actually display their uncertainty.
Yeah, absolutely. It's a really great point. I know even in the Jurassic, we have problems with this sort of thing. It's not just into the Precambrian. It's an old thing. Yeah, it's a really great point. I mean, I mean, I guess the figure that we put up at the moment, right, what we want to do is to try and include as much uncertainty as we can, because so many of these environmental things are changing by multiple orders of magnitude. The hope is that even though things in the inputs are very uncertain, you can still falsify something or other by adding a very large uncertainty window. So yes, and the problem with the duplex reconstructions is that they just have sort of one truth. They don't really have a very good uncertainty window, and it's not very easy to just produce one. What we are doing at the moment is we're tracking all the different emissions from all the different kinds of plate boundary in the model, trying to understand what these are like at the present day, how these could have varied over time, and trying to build uncertainty on top of those.
But
So,
we have even no constraints on the present day for outgassing. The way we estimate outgassing is just matching what we measure in rivers. We don't know how much CO2 is coming out of ridges. We don't know how much is coming out of arcs. And so even trying to do what you're doing for the present is hopeless. So I just be careful about outgassing is the only suggestion.
yeah, I mean, we are doing everything we can. I mean, I suppose the point is to try and take as many different approaches as you can and see which ones agree. So these mechanistically produced models of outgassing, they do have a lot of uncertainties, they have a lot of problems, but they do have some things that we can be fairly certain about, like, high spreading rates in the Cretaceous, for example, is fairly uncontroversial. Right? Or is it? Can we agree on that one?
High spreading rates? Yeah, I think there's quite a bit of disagreement about how to quantify that. And, I think trying to put the amount of error and uncertainty that would exist. So put as an end member, Dave Rowley's opinion on, spreading there. And so there is so little preserved that, and the Mueller group will present these as these certain paleogeographic and ocean spreading, and they're just not actually displaying the uncertainty there. And so to just take those off the shelf and say, this is the world, this is reality, it just doesn't display that uncertainty. So, there's a lot of disagreement about what the Cretaceous change in spreading, change in subduction. And then we don't know if there was increased CO2 outgassing, was it because there was more subduction? Does more subduction actually cause more outgassing? So yes, there's generally agreement that there could have been more spreading, but I don't know how to quantify that.
No, I think it's a very good point. So I guess, this is one of the reasons we're building models like this, because the simplicity of the model means you can run it thousands and thousands of times and test lots of different things. So what we're able to do is to run tests where we don't vary outgassing at all, or where we do some fairly extreme uncertainty analysis on what things could have been. So I guess, I don't want to commit to one view of this, because I think you're right that it is really, really uncertain. But
yeah, and I think that's what's great about your models, is that you can then start to test the uncertainty there and start to play with the fact that we don't know that. And so I think that's fantastic.
I think that's right. I think that's a great point. And I think, similar levels of uncertainty exist for so much other things in the model as well. It is a difficult thing to do.
All right.
Yeah.
Thanks, Francis. Thanks, Paul. Andre, you want to go?
Yeah, Ben, I have great talk. I have a couple questions. Maybe I ask them separately. So one, I like this growth of crustal carbon reservoir, but what does it implication it has? In a way, it means that crust and mantle still didn't reach equilibrium, not in a stable state, and what implication it has in terms of subduction flux and flux coming, carbon dioxide coming from the mantle, or carbon isotope composition of this flux.
Yeah, great point. So this, again, something when you make the shift from working in these Phanerozoic models where we assume that the present day is completely a steady state to trying to do things over 3 or 4 billion years, is that there isn't, we don't know that there is a steady state between the mantle and the surface system. So if we were to look 100 million years, 1 billion years into the future, will the continental reservoirs of carbon continue to grow? So is that assumption that they've sort of reached some stability just something we happen to do for our models? I don't really know. I think there's a lot of things we can test there. I think the sort of traditional geocarb style box modeling approaches have always focused on the surface system, really, with assuming that they're sort of wrapped in a steady state. And when you start to modify that longer term steady state, you can do some weird stuff in the surface system, I guess. So yeah, sorry, that's a really non-specific answer, but I think you can change a lot in these models, essentially.
Yeah, I think it would be interesting kind of to model it, to see how this interaction between mantle and crust for carbon works. And another question, you sort of, I like sort of what organic carbon in low oxygen level become like a passive passenger, so it's sort of get recycled into new bases. But did you think it in terms of phosphorus? Because if you have less oxidizing power, you can also carry this organic phosphorus with organic carbon, exclude it from surface environments, and limit productivity by sort of excluding it.
Interesting. So are you talking about if you're weathering organic carbon in a low oxygen environment, the phosphorus won't get transferred into the ocean. It will end up in the sediments.
So basically, from the time organic matter kind of dead in water column to the time it weathered, it would be exposed to less oxidants, and as a result of it, less phosphorus would be released through remineralization.
Yeah, interesting. Yeah, I mean, I think to some degree we capture that, but probably not correctly, I think would be the answer. I think, again, I think my answer to everything is yes, we should probably look at that. And yeah, I think we should probably look at that.
Because it would be like a feedback that you bring in less phosphorus, less productivity, and when so you kind of maintaining carbon cycle on the same level, except you have this passive compartment where kind of recycling happens.
Yes. Yeah, you're right. So we think we're doing half of that in the model, but we're not explicit because it's things that don't become bioavailable in the model are just not really considered. So I think we're doing half of that, but we're not actually then building up phosphorus. We're just not considering it ever being weathered, I think. Yeah, so it's a great point. I think that's something to look at.
Thanks.
All right. Paul, did you want to go again, or is your hand just still up? I can't tell.
I'd like to make a comment on Greg Vitalik's suggestion that the Neoproterozoic carbon isotope excursions are related to subaerial exposure and pedogenic carbonate and karst, etc. When I first started working in Namibia, being a newcomer to stable isotopes, I was somewhat skeptical that diagenesis hadn't been properly taken into account. And so I intensively sampled all the subaerial, the best developed subaerial exposure surfaces in the Otavi group, which were revealed by stratigraphic mapping and outcrop studies. And I intensively sampled them, and I didn't see any change in carbon isotopes associated with subaerial exposure surfaces and related diagenesis at all. None. Zero.
Yeah, Greg, if you want to join the conversation, go ahead.
Sure. Yeah, Knauf and Kennedy addressed this really quite nicely, and so did several other people. There's quite a strong correlation between carbon and oxygen when carbonates get weathered. It's not that great in paleokarsts because they started up from a marine limestone precursor, and then they were aligned by those meteoric waters. But in paleosols, it's just super tight, like a 0.9 R squared. There's plenty of evidence for meteoric alteration of carbonates associated with those big isotope excursions, and it's in the direction that you'd expect. It all gets lighter. Now, you're not going to see it everywhere. There's going to be some marine and some non-marine. The correlation between carbon and oxygen in carbonates, I think, is a really good indicator of meteoric influence.
Water vapor in the tropics is at sea level is barely fractionated relative to seawater. And the whole Kennedy argument was based on oxygen isotopes. And yet, if you look at the isotopic composition of water vapor, for example, in South Florida, it's less than 2 per mil different from seawater.
Okay, but that's not what counts. That's the weathering. What does the weathering is carbonic acid from CO2 by soil respiration, which is massively fractionated from the atmosphere and the ocean by minus 29 per mil. That's where the difference comes. And the Rubisco enzyme will fractionate simultaneously for light oxygen and carbon in carbon dioxide. That's how you get these strong correlations. It doesn't matter what the air and what the ocean is when it comes to soils, because soils have their own gases that are massively fractionated biologically. Soils can have up to 100
and their type karst in the Kingston Range isn't even an exposure surface. It's a marine flooding surface.
I can't.
No evidence of subaerial exposure there at all.
I can't address that one. The one I know best is the Wanaka Formation, which Nick Christie-Blick has been studying with Sarah Giles, which I find a very convincing paleokarst.
Okay. Well, maybe this got a little far from the topic, and we can.
I think we are.
Yeah.
Anyway,
but thank you both. It's good to hear you both on that.
Yeah, this has been fantastic. I really enjoy what you're doing, Ben. Keep it up.
Yeah.
And thanks for all the suggestions. And if any of you, I want to test a lot of ideas in this model. If anyone has suggestions, mainly like stuff I've got wrong that I need to fix. So all those paleogeographic suggestions, if you can email those over, then we will do some uncertainty analysis where we fix them, I promise.
Your point about the algae, I think, is very important because haptified algae and alveolate protists have a major effect on cloudiness in the marine realm. And so if the DMSP production was much less, then the marine surface albedo is going to be a lot lower before DMSP production evolved.
That sounds like a good point. Yeah, no, thank you. Yeah, thank you everyone for having me. I hope that was interesting.
Yeah, thanks, Ben. I think we've had you on for long enough and questioned you quite a bit. It was really a lot of good discussion. Thanks everybody for being here. And we'll see you guys back next week. Roman is here today, but he's going to give a talk next week. So, all right, everybody, take care and see you next week.
And bye.